When you think about the circus, what first comes to mind? The three rings, of course. The circle is quite prominent under the big top. In fact, the circle and the circus go back a long way. The word circus dates back to ancient Rome, where the Circus Maximus was a huge circular structure used for a wide variety of public attractions, including spectacles intended to end in death. Fortunately, the stakes aren't as high nowadays. As for the circular rings, they date back to 18th century England, when Major Philip Astley, a trick horse rider, discovered that if his horse galloped in a circle while he stood on its back, the centrifugal force would keep him from falling off. In doing this, Astley traced the first circus ring. A circle is defined mathematically as the set of points, each of whose distance from a fixed point is a constant. When you draw a line out from a point, it's called a radius. If you sweep the radius around a full 360 degrees, the end of the radius traces out a circle. You can get the circle another way. It can be derived from another geometric shape, the cone. And the circle is only one of a very important family of curves called conic sections. The conic sections made their mathematical debut in ancient Greece. The most comprehensive treatment of the curves was written around 200 BC by Apollonius, a mathematician known in antiquity as the Great Geometer. In a huge 8-volume work called the Conics, Apollonius proved that these curves, the circle, the ellipse, the parabola, and the hyperbola, could be derived from a single cone. The Conics was so complete that we hardly know more about conic sections today than Apollonius did 2,000 years ago. To get the conic sections, all you need is a cone and a plane. To get a circle, take the plane and intersect it with a cone horizontally, parallel to the plane at the bottom of the cone. Now, if the cone remains stationary while we tilt the plane, the circle becomes an oval or an ellipse, a sort of elongated circle. An ellipse can also be defined as the set of points, the sum of whose distances from two fixed points is always the same, a constant. Each of these fixed points is called a focus. An easy way to draw an ellipse is to tie a string to two stationary pins, which represent the foci. Then take a pencil, put it inside the string, and trace a figure like this. Since the string is a fixed length, the sum of the distances from the foci is a constant. The result is an ellipse. Now, a circle is a special case of the ellipse, because if we bring these two foci together, and we repeat the procedure, we get a circle with both foci at the center. So every circle is actually an ellipse when seen from a different angle. Take a look at this cup of cola. The surface of the liquid is a circle, but when I tilt the cup, the circle turns into an ellipse. This close relationship between the circle and the ellipse misled astronomers for centuries. To early astronomers, the heavens were an expression of divine order. In this 1543 woodcut from Martin Luther's Bible, God the Orderer oversees the universe. The earth is fixed at the center, and the sun, moon, and stars revolve around the earth. This earth-centered or geocentric view dates back before the ancient Greeks. The planets were believed to be encased in solid, transparent spheres, whose rotation accounted for their motion. The Greeks believed that the universe was perfect, and therefore only the sphere, the perfect solid, and the circle, the perfect curve, could be used to explain planetary motion. In the 2nd century AD, the Greek astronomer Ptolemy, seen here with the muse of astronomy, replaced the notion that planets moved on concentric circles and spheres with an ingenious geometrical scheme. Ptolemy, like many astronomers before him, sought to explain the irregular motion of the planets. They seemed to slow down, stop, and reverse their paths as they moved through their orbits. Ptolemy accounted for this complicated motion by breaking it down into its constituent parts. He developed a system where small circles, called epicycles, moved on larger circles. Here's the basic motion of an epicycle. The planet Q moves with constant speed around a small circle, an epicycle, while the center of the epicycle, P, moves with constant speed around a larger circle, called a deferent. The deferent was centered on the stationary Earth. The circular motion of the epicycle and the deferent combined to produce this kind of a pattern. In order to preserve the ideal that planets moved on circles, Ptolemy adapted the basic epicyclic scheme to the specific motion of each planet. For example, the center of a planet's deferent, O, is not the Earth's center. It's situated a short distance away at a different point for each planet. The Sun doesn't have an epicycle, but its deferent revolves around its own central point, S. The Moon does have an epicycle, but while the epicycles of the planets move in the same direction as their deferents, the epicycle of the Moon revolves in the opposite direction. By the time he'd completed his design of the universe, Ptolemy's scheme included 40 cycles and epicycles. Astronomers believed in Ptolemy's Earth-centered universe for another 1,300 years. This map of the heavens from the star atlas of Andreas Cellarius remains as an artistic record of the era. In the mid-1500s, the astronomer Copernicus posed the first serious challenge to the geocentric view. He claimed, among other things, that the sun was the center of the universe. At the time, this belief was not only radical, it was considered to be heretical. Over 100 years after Copernicus introduced the idea, Galileo would be imprisoned for holding it. In the early part of the 17th century, astronomer Johannes Kepler wished to prove the Copernican theory. Like his predecessors, he wanted planetary data to fit into a scheme of circular orbits. Well, Kepler became fascinated with the orbit of the planet Mars. He spent many years analyzing an enormous amount of data on the planet, carefully collected by the Danish astronomer Tycho Brahe. Beginning his observations when the Sun, Earth, and Mars were aligned, Kepler charted the positions of Mars over time relative to the Earth. Although he was able to fit Mars into an epicyclic orbit for 10 of Brahe's observations, when he added 2 more points, he found a large discrepancy. Finally, after nearly 6 years of frustration, Kepler abandoned the idea of epicycles. This led him to one of his greatest findings. The orbit of Mars was not a circle, it was an ellipse. The famous results of his efforts are known as Kepler's laws of planetary motion. The first law says that planets follow an elliptical path with the Sun at one focus. Kepler's second law is known as the law of equal areas. The law states that during a given time interval, a line from a planet to the Sun sweeps out an equal area anywhere along its elliptical path. Or in other words, equal areas are swept out in equal times. Once Kepler established the laws of planetary motion, astronomers were free to turn their attention to comets. In 1684, astronomer Edmund Halley was trying hard to understand the paths of comets. He knew that Isaac Newton had shown that Kepler's equal area law was a consequence of the law of gravitation. Newton concluded that comets follow the same laws as do the planets. Indeed, Newton actually calculated the path of the comet of 1682. Halley, excited by Newton's work, convinced Newton to publish it. In fact, Halley financed and acted as editor of Newton's book, The Principia, in which the theory of gravitation was worked out. It's possible that without Halley's influence, this book, one of the greatest scientific works of all time, might not have been published. Halley applied Newton's methods to an analysis of cometary records of the past. He concluded that the comets of 1531, 1607, and 1682 were really the same, and then boldly predicted the end of the year 1758 for its return. Since then, the comet has borne his name. In this picture of the solar system, the orbit of Halley's comet can be observed on the right as a flattened ellipse. The outermost ring represents the orbit of Pluto. The next one in represents Neptune's orbit. At its farthest point from the Sun, Halley's comet sweeps beyond Neptune's orbit. The comet travels an elongated elliptical path that is tilted from the orbits of these planets. It spends most of its time in the outer solar system, traveling inside of the Earth's orbit every 76 years. Moving slowly when farthest from the Sun, the comet picks up speed as it approaches the Sun. The conic sections are probably best known for their reflective properties. But before talking about the conic sections, I'm going to illustrate the property of reflection with this snooker table and this billiard ball. Whether you're using rays of light, sound waves, or a billiard ball, the way in which something reflects always adheres to the same principle. The angle of approach, or incidence, equals the angle of reflection. So if the ball approaches the cushion at this angle, it will reflect off it at the same angle. Works with this angle too. Assuming there's no spin on the ball, no matter what the angle of incidence, the angle of reflection will be the same. Although the crowd down at the pool hall doesn't sit around talking about Newtonian physics, they use this principle in every bank shot. Now, with a flat surface like this, it's easy to predict how the ball will bounce back. But when we start talking about curved surfaces, the angle of reflection is not quite so easy to visualize. In the case of the ellipse, a ray which originates from one focus and reflects off the ellipse will always return to the other focus. This holds true for any kind of ray, or for a physical object, like a ball. This property is good to know if you're playing pool on an elliptical table. To play elliptipool, shoot the ball through one focus, bank it anywhere off the side, and it'll end up at the other focus, the hole. Now, that may not seem too remarkable, but if the ball doesn't travel through the focus, it will never fall into the hole. Watch. Of course, the game gets a lot more complicated when the table is filled with balls, but just for fun. Who said math wasn't useful? The Mormon Tabernacle in Salt Lake City is perhaps best known as the home of one of the world's most famous choirs. But the structure's fame extends beyond that. Back in the 1860s, the tabernacle was built with an elliptical ceiling that exhibits the reflective property we've been talking about. Places with elliptical ceilings are known as whispering galleries. Here's why. This woman is about to drop 3 pins. Next, a nail. She's positioned at one focus of the ellipse, approximately 170 feet away from the cameraman and microphone. Only someone standing with the camera and microphone at the other focus will be able to clearly hear the sounds from so far away. This is the same property of reflection we saw earlier. The sound waves bounce off the elliptical ceiling and go directly to the other focus. World War II. German bombers are headed for the English coast. Before they know it, they're under attack by a British Spitfire. This single-pilot fighter was a formidable weapon for the Allied forces. It was renowned for its facile maneuvers and quick acceleration. The plane's success was due in part to its aerodynamically superior elliptical wing, which had ample room for weapons like 20mm cannons. The design was based on the first three-dimensional wing theory ever put forth. Previous theories had considered only the two-dimensional problem of the airfoil or cross-section of the wing. But the shape of the wing, its outline as you look down on it, affects its lift and drag as well. For all the wing shapes that could provide enough lift for the plane, the elliptical design has the least drag. The members of the King Charles Troop aren't flying, but they are doing some pretty fancy moves on unicycles. It takes a lot of stamina and power for professional acrobats to maneuver these cycles. Performing stunts, like riding backwards or at breakneck speeds, requires a great deal of skill. Now, for ordinary people like you and me, riding even a regular bicycle might be more taxing than we'd like to admit. An alternative design uses an elliptical chain wheel. It allows bicyclists to use the power of their legs more efficiently when riding at slow speeds. With a traditional circular chain wheel, it's hard to turn the crank when the pedals are in this position. But when the pedals are horizontal, it's a lot easier. Unlike the circular design, the elliptical chain wheel changes the gearing throughout the pedaling cycle. When the pedals are vertical, the effective radius of the chain wheel is short, and it's easy to pedal. This way, there's less wasted effort. When the pedals are horizontal, the radius is longest, and the cyclist can push hardest when it's most effective. To demonstrate the next conic section, the parabola, Captain Christopher, the human cannonball. Captain Christopher's curve generator. Any projectile, human or otherwise, follows the path of a parabola. Captain Christopher's parabolic flight. To get a parabola, slice a cone with a plane parallel to the slant of the cone. A parabola can also be defined as the set of points whose distance from a fixed line, the directrix, and a fixed point or focus are the same. An extraordinarily useful characteristic of a parabola is its reflective property. When parallel rays strike a parabolic curve like this, they reflect through the focus. So all rays coming in parallel to the axis of the parabola end up at the focus. This property works in reverse as well. The car headlight makes use of the reverse reflective property of the parabola. Light from a bulb at the focus bounces off the curve and reflects out straight in front of the car in parallel beams. This gives the car good directional lighting. Parabolic surfaces are vitally important in the design of the modern telescope. This reflecting telescope at the Harvard-Smithsonian Oak Ridge Observatory was built in 1933. At the time, it was the world's largest, but by today's standards, it's mid-sized. The telescope has been used to measure the positions of over 100 comets, including Halley's, and 1,000 asteroids. Dr. Ronald Shorn of Sky and Telescope magazine explains how the Newtonian arrangement of this telescope works.
This is a 61-inch reflecting telescope, and at the bottom of this telescope tube is a large parabolic mirror 61 inches in diameter. Its surface is covered with a very thin film of aluminum, and the light from the sky gets reflected off that and back up towards the front of the tube. Large telescopes like this can be used in several different ways, and one of them was invented by Sir Isaac Newton of gravity fame. In that form, a flat mirror at the top of the telescope reflects the light to a focus here, where you can photograph it or do anything you want to with it.
You don't need mirrors or complex technology to make practical use of the parabola. The curve of my hand can serve the same function as the collecting mirror in a telescope, only this time the curve is collecting the sound waves and focusing them in my ear. And the curve of my hands serve the opposite function here. With my mouth as the focus, my hands send the sound waves out in a parallel fashion, just the same way that light is directed out from an automobile headlight. The parabola is also useful in designing bridges. If a horizontal roadway is suspended from a cable by many vertical supports, the cable will take on the shape of a parabola. Stress will then be distributed uniformly throughout the thickness of the cable. This way, every strand of the cable contributes equally to support the weight below. Bridges with parabolic arches work on the same principle. This bridge is supported from below by beams shaped like parabolas, which are ideal for supporting a uniform horizontal load. The strength of the bridge is due to its form rather than its mass. In order to derive the final conic section, the hyperbola, we need to learn more about the precise definition of a cone. Take a fixed plane with a circle drawn on it. Then draw a line through the center of the circle, perpendicular to the plane. Choose a point V on this line, with V not on the given plane. Now the surface, consisting of all the lines that pass through both V and the circumference of the circle, is a cone with vertex V. The vertex separates the surface into two parts, called naps, so a mathematical cone is really two common cones, nose to nose. The cone we used for the circle, ellipse, and the parabola is technically called a truncated cone. We used the truncated cone to describe these conics because the plane that slices the cone is positioned in such a way that it only intersects one nap. The hyperbola is the conic section that results from intersecting both naps of the cone with the plane. It's therefore a curve with two branches. The hyperbola is also defined another way. We start with two foci. Now, pick a point on the curve. Find the difference between the distances to the two foci. In this case, it's 8. Choosing another point, we find the difference is also 8. The difference is a constant. You see, the hyperbola is the set of points with a fixed difference of distances to two foci. For the other branch, the same condition applies. All of the conic sections can be defined in still another way. Remember, a moving point traces out a parabola if its distance from a fixed point is equal to its distance from a fixed line. In other words, the ratio of these distances is 1. In general, if the ratio of the distance from any point on the curve to a fixed point divided by its distance to a fixed line is constant, the curve is a conic. This constant is called the eccentricity of the curve. So the eccentricity of a parabola is 1. If the eccentricity is less than 1, the curve is an ellipse. And for a hyperbola, the eccentricity is greater than 1. The Clown Jazz Band contains the best example of the hyperbola that we can find here at the circus. Look at the bells on the trumpet and the trombone. The curves are hyperbolic. Sound or light rays emanating from one focus reflect off a hyperbolic surface as if they were coming from the other focus. The hyperbola has the ability to scatter rays over wide areas, unlike the ellipse and parabola, which tend to focus rays. It's this ability to scatter rays that makes the hyperbolic shape useful in such things as street lamps and space heaters. The telescope at the Oak Ridge Observatory also employs a hyperbolic mirror in one of its forms. Dr. Sean demonstrates.
When a reflecting telescope is used in the Cassegrain form, as this one is here, the primary mirror at the bottom of the tube reflects the light up to the top of the tube. And there, a smaller hyperbolic secondary mirror reflects the light back down through a hole in the primary mirror to a focus here. In this case, this auxiliary equipment sends the data on the star being observed through these cables to a computer in the room next door.
In the Cassegrain system, the converging light from the parabolic mirror hits the convex side of the secondary hyperbolic mirror and is reflected back toward the primary. The hyperbolic mirror intercepts the light before it reaches the parabola's focus and folds the light path. The precise positioning of the mirrors working together in the Cassegrain telescope causes the light to focus at the photographic plate or image sensor. A great advantage of the Cassegrain system is one of physical size. It can be much more compact than the standard reflecting telescope. Size was a critical consideration in the design of NASA's Hubble Space Telescope, which could only be as wide as the shuttle bay. The Space Telescope's primary mirror is 8 feet in diameter, about 3 feet wider than the Oak Ridge mirror, and the hyperbolic secondary mirror is 13 inches in diameter. Unimpeded by the Earth's atmosphere, the 12-ton Space Telescope can observe 7 times further than the best ground-based telescope, even though it's not the largest. The Mount Palomar telescope in California is more than twice its size. In its lifetime in space, the telescope will search for planets outside our solar system, black holes, and galaxies formed not long after the Big Bang, all previously unobservable mysteries of the universe. The usefulness of the hyperbola is not limited to stargazing. Here on Earth, a hyperbolic surface in 3 dimensions is an important shape in building physical structures like the cooling towers of nuclear power plants. When designing these towers, engineers have two problems. The structures must be able to withstand high winds, and they should be built with as little material as possible. The hyperbolic form solves both of these problems. For a given diameter and height of a tower and a given strength, this shape requires less material than any other form. A 500-foot hyperbolic tower can be made of a reinforced concrete shell only 6 or 8 inches thick. In this case, the curve of the tower is wider at the bottom when more strength is needed. In the trumpet, the curve is wider at the end where the sound waves are to be dispersed over a wide area.
So the conic sections, discovered more than 2,000 years ago, are becoming more and more useful as technology advances and takes advantage of their important properties. But technological advances aside, sometimes the oldest uses are the best uses. Hey, how about some cotton candy over here?